Normally in classical mechanics, after we define position and figured out a formula for it, the next thing we would move on to would be velocity. So, sort of logically, it seems like the next step in quantum mechanics would be to define the quantum mechanical analog to velocity. So let's sort of define some basic things. So in classical mechanics, we have position x of t. And then when we go to quantum, what we find is that the analog to that is the wave function psi of x comma t. So, sort of evidently, what we will want after that is the velocity v of t is equal to dx over dt. And evidently, what that implies is that in quantum mechanics, apparently, we want something akin to the partial with respect to time of psi. However, this thinking about it conceptually should sort of concern us a little bit, because one of the things that we sort of implied by defining the position of a particle using a wave function is that a particle in quantum mechanics evidently does not have a well-defined position. Because of the fact that psi of x is a probability density, our particle has a probability of being in certain areas, a slightly higher, slightly lower probability of being in another area, etc., but there is no well-defined probability. And since there is no, or sorry, not probability, position, and since our particle has no well-defined position, evidently the velocity for that particle must also not be well-defined. So sort of this trying to create analogs to this sort of doesn't really make sense, and the wave function doesn't really help us in trying to actually define a well-defined velocity for our particle. Now, instead, we do have something that is sort of very close as an analog to definite values, and that actually is the expectation value of position. So we define the expectation value of x to equal the integral of x mag psi squared dx. And we sort of define this over all of space. So in 1D, that's just from negative infinity to positive infinity. So evidently, if we define, this does give us a well-defined value. This is the average or the expectation value of x. And sort of if we analyze the rate at which this changes, then we get something that is akin to a definite value of velocity. So if we say that d over dt of the expectation value of x, well, this will effectively give us partial with respect to time of x mag psi squared. Whoops. And this is something that we can sort of solve. This quantity evidently, or looks like it will give us a definite value. So sort of the first step that we can do is we can try to solve this and see if it sort of gives us any information about what exactly we're sort of looking for. So now that we're kind of at this point and our goal is to solve the derivative of the expectation value of x with respect to time, we can recognize that x can just move out of our partial with respect to time because x has no time dependency, and now it is just a partial with respect to time of mag psi squared. And back in 1.4, when we were talking about normalization, we sort of proved that mag psi squared kind of remains normalized for all of time, and one of the things we calculated was this expression, the partial of mag psi squared with respect to time, which equals partial with respect to x of this entire thing over here. So we can just plug that in. So we're going to write d with respect to time, so derivative of time of the expectation of value of x is equal to the integral from negative infinity to infinity, and then we're going to move the x from inside, which is this one right here, we're going to move that out. So x and then this entire thing over here, and we can actually just copy paste that for simplicity. So this whole thing, and then all of this with respect to x. And instantly, we can simplify this a little bit, and we can move our IH over 2m outside of our integral, just because it has no dependency on any variable, it's just a constant. So this equals I times h bar all over 2m times the integral from negative infinity to infinity of x times partial with respect to x of, and here we're going to copy paste this again just for simplicity, this entire expression with respect to x. And since there's sort of a partial with respect to x in our integral, we can sort of get rid of it by using integration by parts. So we're going to do that right now. We're going to say that u is equal to x, which implies that du is just dx. And then for v, we're going to say that dv is equal to sort of our right term over here, partial with respect to x of this entire mess. And what that means is that if we take v, and also let's add a dx at the back, so v is simply equal to the term itself. So if we write this out, then d over dt of the expectation value of x is then equal to, and we start off with uv, so we start off with x multiplied by this whole mess, then evaluated at negative infinity to positive infinity, and then subtracted by integral of v du. So subtracted by the integral from negative infinity to positive infinity of our v expression and du, which is just dx. Now, earlier on, one of the conditions that we made for psi was that we sort of required it and its complex conjugate to both go to 0 as x goes to plus or minus infinity. And the reason why we required that is because we required psi to have sort of a finite area under the curve so that we can normalize it properly. If psi does not go to 0 as x goes to plus minus infinity, then its area would be infinite, and that would result in an infinite probability, which does not make sense and is not physically realizable. So one thing we can recognize here is that both of the terms that come as a result of this first sort of integration, both of them, this left one has a psi star term and the right one has a psi term. So both of these terms have to go to 0 as we plug in x equals infinity and negative infinity. So automatically, as a result of that, this term simply cancels out and we no longer have to worry about it. So we can just say that d over dx is equal to, and I actually forgot to include the IH over 2m. So we're just going to do that and move it right here. So what this equals is negative, and then IH over 2m times the integral, times the integral from negative infinity to positive infinity of this big mess here with respect to dx. And at this point, we sort of have two different terms, and one of the things we can actually do is that we can reduce this from two terms to one term by once again using another integration by parts. So I'm going to do this on the second term right here. And what I'm going to say is that, okay, let's set u equal to psi. So that means that du, whoops, that's a messy d. Say that du is equal to partial of psi with respect to x. And then we do the same thing for v. We say that dv, whoops, we say that dv is equal to partial psi star, or psi conjugate with respect to x, dx, which automatically implies that v itself is simply equal to psi star. So if we sort of use this integration by parts on our second term while leaving our first term alone, what we get is that d over dt of our expectation value of x is equal to negative I h bar over 2m as before, and then our integral from negative infinity to infinity of our first term, psi star partial psi with respect to x dx, and then we split our integral, so subtracted by, and now we use our function, so uv, we start with uv, so psi star and this is going to be evaluated at plus or minus infinity, psi star, subtracted by the integral of v du, so subtracted by the integral from negative infinity to positive infinity of v, which is just psi star, du, which is partial psi with respect to x, dx. And once again, we sort of have this requirement that psi and its complex conjugate needs to go to 0 at plus minus infinity, so we can automatically kind of get rid of this. So what this becomes is, and let's sort of make our canvas a little bit wider. This implies is that this expression is equivalent to, and we're going to do the same thing at the front because nothing happens at the front. So this whole thing is equal to this same thing sort of at the beginning, and then the minus sign kind of cancels out, the minus sign becomes a positive, so this becomes plus the integral from negative infinity to positive infinity of psi star partial psi with respect to x. And since this is basically the same integral, we can just combine this and add a 2 at the front. So this whole thing is therefore equal to negative I h bar all over 2m, or this time just m, because there's the 2 gets canceled out now, and then the integral from negative infinity to infinity of our psi star partial psi with respect to x dx. And this is sort of this is the derived expression for the rate at which the expectation value of x changes. So at this point we've sort of defined our expectation value of x, and then the time derivative of our expectation value, which we will call expectation of velocity. And this is sort of the closest that we can get to position and velocity in quantum mechanical terms. In other words, this is sort of the best that we can do. Our particle doesn't actually have a well-defined position, and so as a result of that, it doesn't really have a well-defined velocity either. So we're sort of stuck with the velocity of the expectation value for position instead. Now, at this point, I'm actually going to, or Griffiths is going to sort of make a claim, and we can't really prove this claim right now. Later on, we will sort of see why this is important, but Griffiths is going to claim that, Griffiths will claim that mathematically it will be much easier for us in the future if we used the expectation value of momentum instead of the expectation value for velocity. And for now, we are unfortunately just going to have to accept this. The reason why this is true will be made clear I think as soon as next section. If not next section, then next chapter definitely. But right now, we're just going to sort of accept this. So let's kind of sort of calculate the expectation value of momentum, and this is actually very trivial because we sort of already know that the expectation value of momentum, well, we know that momentum is mass times velocity, so the expectation value of momentum would just be the mass times the expectation value of velocity, which we sort of solve for up here in green, and we see that there's a mass in the denominator, so this simply just equals negative I multiplied by h bar times the integral from negative infinity to infinity of psi star partial psi with respect to x dx. So this is sort of, these two are in fact our most important quantities. This and then also our expectation value for position. And once again, we don't really know why, as of right now, why we're using momentum over velocity, but in the future, it will be much more mathematically convenient for us if we used momentum instead of velocity. So for now, we're just going to accept that this is sort of the way we're supposed to do it. Now, Griffiths is once again going to make a second sort of claim, and the second claim is he's going to introduce what are called operators. And once again, we sort of won't actually know why exactly we're doing this for now, and we're not going to really be able to prove it right now. And in fact, we're not going to be able to prove why Griffiths does things the way he's doing right now until maybe like halfway through the book when we start introducing eigenfunctions and linear algebra into the math. But until then, we are going to have to also make sort of this second assumption, and we're going to say that we're going to introduce operators, which is basically these expectation values of x and expectation values of p. We're going to say that x and p are what are known as operators. So x and p are known as operators. And what happens is we can rewrite these expectation value functions sort of with this whatever the operator term is sort of sandwiched in the middle. So originally we had our function expectation value of x equals integral negative infinity to infinity of x psi star psi dx. And what I'm going to enforce instead is we're going to sort of make this claim that we're supposed to write it instead as the expectation value of x being equal to the integral from negative infinity to positive infinity. And this time we're going to sandwich the x in between psi star and psi. So we're going to say this is equal to psi star and then multiplied by x, which is our operator, times psi dx. And here, this notation isn't really that important because everything commutes with each other anyway, so this is sort of exactly the same thing as writing it as x on the left. However, for momentum, things go a little bit differently. We will see here that momentum, if we sandwich everything in the middle, it becomes p equals the integral from negative infinity to positive infinity of psi star. And if we sandwich sort of everything in the middle, what we see is that, well, in this case, it's negative I h bar times partial with respect to h, or with respect to x. So negative I times h bar times partial of x multiplied by psi dx. And here, this is sort of, this with momentum, we kind of get a more clear image of what exactly we mean by operator. So what we're doing is we're taking everything and basically operating it onto psi on the right. So we're sandwiching it in between psi star and psi, with psi star specifically on the left and psi specifically on the right, and this negative I h bar partial with respect to x acts on psi. So that's why we sandwich it in between, because if we sandwich this, if we didn't sandwich it in between, then this partial with respect to x would act on both psi star and psi, in which case we would have to use product rule and everything would be wrong. So this is just a very specific rule for the way we write out our integrals. And once again, the reason why we're doing this isn't exactly clear right now, but it will sort of make our math much simpler, and as it turns out, later on we will see why we are doing this. But for now, unfortunately, we're just kind of going to have to accept the way Griffiths does things and sort of take it as fact and face value for now. So from this, what we can see is that apparently, if we generalize this, evidently the expectation value of anything, Q, is in fact equal to the integral from negative infinity to infinity of psi star multiplied by whatever operator represents Q times psi dx. So what happens is that Q is some term that has an operator that defines it, and this operator acts on psi inside of our sort of integral. And as we see up here, the operator representing x is just x itself, and the operator representing p is apparently negative I h bar partial with respect to x, and we sort of calculated this. We don't really know why it's this way, but we sort of calculated it, and the math tells us that this is how it is, so we're just going to accept it as it is. And evidently, if we generalize this, then any expectation value of Q, any value apparently has a corresponding operator, which does in fact sort of the expectation value of sort of plugs in nicely like this. And actually, we can prove this generally because, as it turns out, in physics, any complicated quantity can be broken down into position and momentum. And this is true for anything. You can sort of think up your own sort of complicated expressions, and you can always break them down into position and momentum. Examples of this include kinetic energy, for example. T equals 1/2 mv squared. And, well, we know how to define v in terms of momentum, because we know that P equals mv. So we know that sort of P is equal to mass times velocity. So that implies that velocity equals just momentum over mass. And we can sort of plug this back in, and T becomes a function of momentum. Same thing. So as a result of that, what we're really saying is that any quantity Q is actually a function of position and momentum. And we won't really prove this, but if you sort of want to like kind of confirm this, you can just think of any physical quantity, momentum, linear momentum, angular momentum, energy. Basically anything can be sort of devolved into x and p. And since we know that x is just x in operator format and p is negative I h bar partial with respect to x in operator format, we can sort of just like put everything in the middle in terms of x and p, and then devolve our p into like negative I h bar partial with respect to x, and this sort of allows us to find the expectation value of any quantity by defining it in terms of operators.